Hey guys, this is Mike Lang and Harmony Cole. Today we're going to be talking to you about black holes and antimatter. Now first off, let's talk about black holes. Now the official definition of a black hole is an area of space-time that exhibits extremely strong gravitational effects. So strong, in fact, that nothing, not even light, can escape from it. But you knew that. Here's something you probably didn't know. Albert Einstein first predicted black holes in his 1960 theory of general relativity, without having any prior observations or information about their existence. American astronomer John Wheeler, however, was the first person to observe black holes in 1971. Now, contrary to common belief, you actually cannot see black holes. So it would look exactly like this. You cannot see anything except black on that sheet. Like I said before, not even light can escape the gravitational effects of a black hole. Then how do astronomers study black holes? There's actually two ways to observe a black hole without actually seeing it. The most obvious way to observe a black hole is to see its effect on nearby matter. Matter within the reach of a black hole gets distorted and slowly sucked towards the center. Another less obvious way of observing a black hole is through the detection of radiation and X-ray emissions. When a gravitational force of a black hole acts on matter, a large amount of radiation and X-ray emissions are released. Astronomers can observe the release of these emissions and determine the location of a black hole. Now, what exactly do black holes do? Most people know that black holes attract matter, and to an extent that's correct. Scientists do prefer the word attract instead of suck in matter. So essentially, what black holes do is they use their incredibly strong gravitational force to attract all surrounding matter. But what happens when matter reaches the center of a black hole? Unfortunately, I cannot answer this question for you. Because black holes cannot be seen, there's currently no way of observing what happens to matter once it enters the center of a black hole. What we do know from observations is that the gravitational force of a black hole actually superheats all matter that approaches it. The prevailing theory about black holes and how they affect matter states that all matter is most likely condensed into one fixed point about the size of a single atom, after it is superheated, of course. So essentially what black holes do is they attract matter with their very strong gravitational fields and most likely compact all this matter into a single fixed location. Now black holes actually do have different components to them. The farthest most point of a black hole is called the event horizon, so right around here. Now the event horizon is the reach of a black hole, so to speak. Once matter is inside this event horizon, it cannot exit because of the extremely strong gravitational effects. It is under the influence of the black hole. Inside the event horizon, there are actually two components. The first is the accretion disk. This disk is composed of stellar material that is spiraling towards the black hole. All matter that is spiraling around a black hole is considered part of the accretion disk. Another part is called the egosphere. Now this part you actually cannot see because what this is actually distorted space-time. Because of the strong gravity, space-time itself actually gets distorted due to black holes. Now the final portion of a black hole is called the singularity. This is the center of a black hole, so right about here, that very dark spot. We actually cannot see inside the singularity. This is the spot where matter is believed to be compressed into the space of a single atom. Now, not all black holes are actually created equally. There are currently three types of black holes. The smallest are called miniature black holes. Now, miniature black holes have never officially been observed because of their incredibly small size. But Albert Einstein's theory of general relativity supported the existence of these tiny black holes. They are predicted to be the size of only a few atoms, yet have the mass of a very small planet, such as Mercury. Now, the generic black hole that are commonly thought of are called stellar black holes. Stellar black holes form when very, very massive stars collapse upon themselves once their lifespan is complete. Only stars with incredibly large masses can form black holes. Now, supermassive black holes are the largest type and form the same way stellar black holes do. However, supermassive black holes are much older than stellar black holes, thus allowing them to have more time to expand and trap matter. Now that you guys know a little bit of black holes, let's switch over to antimatter.
Okay. The first thing you need to know about antimatter is how to understand antiparticles. Every elementary particle has a partner particle, the antiparticle. Together they share many of the same characteristics, but many are opposite. For example, the mass and weight can be the same, but the electrical charge is reversed. The particle referred to as the anti-electron has a positive charge opposed to the negative charge electrons are known to possess. Antimatter behaves in the same way with gravity as regular matter. Though when a matter particle meets an antimatter particle at a high-speed collision, they will destroy each other completely. This is called annihilation. It is also believed by fundamental physicists that there should be the same amount of matter as there is antimatter. So where is it? It's challenging to come across because distinguishing antimatter from regular matter is extremely difficult due to their similar characteristics. A British theorist by the name of Paul Dirac predicted antimatter in 1928. He discovered his prediction after combining Einstein's special relativity equation with quantum mechanics. Any way he tried, the equation would work with electrons possessing either a negative or positive charge. So from there on, he decided every particle has a mirror image. After the prediction made by Dirac, a scientist named Carl Anderson confirmed antimatter. He shot gamma rays at atoms and ended up creating electron-positron pairs. Today, the record to hold and study antimatter is a total of 17 minutes. It's extremely difficult, and it's only able to be done in a large hadron collider. It has also been predicted that 1 gram of antimatter annihilating a gram of regular matter would release 2 times the amount of energy as the nuclear bomb on Hiroshima, though researchers are very far from finding or creating 1 gram of antimatter. An antimatter black hole and a regular black hole are actually very similar. They have the same mass, charge, and angular momentum. Some believe that a giant explosion of antimatter could be created by the acceleration of particles around massive black holes. So why do we live in a matter-dominated universe?